If you've ever played around with reinforcement learning, you know the classic headache. Does my agent stick with what it knows works, or does it take a risk and explore something new that might be even better? It's the core trade-off. Well, today, we're going to level up from that basic problem and dive into 3 advanced methods that make exploration not just random, but truly intelligent. So here's our game plan for this explainer. First, we'll see why just wandering around randomly isn't going to cut it. Then we'll unpack 3 progressively smarter solutions. A really cool psychological trick that uses optimism, a statistical method that cleverly bets on uncertainty, and finally, a totally different approach that learns preferences instead of just values. To wrap it all up, we'll put them side by side so you know exactly which tool to grab from your toolkit and when. Okay, so our journey starts with the old standby, the one everyone learns first, Epsilon Greedy. It's a real workhorse for sure, but it has one massive weakness. See, when it decides to explore, it's completely and totally random. Imagine you're picking a new restaurant. Epsilon Greedy would look at a place with terrible reviews you've never been to and a place with rave reviews you've never been to and treat them as equally interesting. It has no sense of which unexplored options are actually promising. And that brings us to the big question for today. Can we do better than just blind, random stumbling? Can we teach a machine to make its exploration choices more strategic, more informed, more intelligent? Well, the answer is a big, resounding yes. Let's dive into how. Our first advanced technique is less of a complex algorithm and more of a brilliant, kind of counterintuitive psychological trick. It's called optimistic initial values, and it basically encourages exploration by forcing the agent to start with some wildly high hopes. The core idea is just so simple, and it completely flips the usual approach on its head. See, normally, we start by setting all the action values to 0, right? Assuming we know nothing. This method says, nope, let's do the exact opposite. We're going to pretend every single option is incredible. We initialize their values to a super optimistic number, say +5, a number we're almost certain is higher than any real reward we'll ever get. And this one little change sets off a really clever chain reaction. So how does this actually play out? Well, picture this. We set all the initial values to +5. The agent, being greedy, picks one of them, expecting this amazing reward. But the real reward it gets is, let's say, just +1. All of a sudden, its estimate for that action plummets. It's disappointed, you could say. But here's the clever part. All the other actions still have that shiny +5 estimate. So the agent is basically forced to try them, hoping they'll live up to the hype. This cycle of disappointment and trying something new continues until every single action has been tested multiple times. It forces this really thorough exploration right at the beginning, before the agent starts to settle down. And here is the proof in the pudding. Take a look at this graph. The blue line is our optimistic agent. You see how it actually does worse right at the very beginning? That's that period of intense, forced exploration, where it's trying everything. But because it learns so much during that time, it quickly figures out the best action and just skyrockets past the standard Epsilon Greedy method, that gray line. It's a classic case of taking one step back to take 10 steps forward. A short-term hit for a huge long-term win. All right, that optimism trick is pretty slick. But you might be thinking it's a bit of a hack. So let's move on to something more principled, something grounded in statistics. It's called upper confidence bound, or UCB for short. And this is all about making a calculated bet on uncertainty. So what's the big problem UCB is trying to solve? Think about picking a movie to watch. You have your favorite movie, that's the greedy choice. But then there's that new indie film that everyone's buzzing about. You haven't seen it, so you're uncertain, but its potential to be your new favorite is really high. UCB turns that intuition into math. It says we should explore strategically, focusing on actions that are either already good or actions that we're really uncertain about, because they just might be the next big thing. Okay, here it is, the formula that makes the UCB magic happen. Now, I know equations can look a little intimidating, but I promise you the idea behind this is super elegant and it just makes sense. We're going to break it down piece by piece. The gist is, for every single action, the agent calculates a score using this formula. Then, it just picks the action with the highest score. Easy. As you can see, the score is basically made of 2 big parts. Let's start with the first one. This first term, Q sub t of A, should look really familiar. It's just the current estimated value of that action. It's what our agent thinks the action is worth based on past experience. This is the exploitation part of the formula. It favors the actions that we already know are good. Now for the fun part, the second term here is the exploration bonus. It starts with a natural log of t, which is just the current time step.
All you really need to know about the logarithm here is that it's a number that always goes up as time goes on, but it goes up more and more slowly. This basically gives our agent a gentle, lifelong curiosity that encourages it to keep exploring, forever.
And here's the real genius. That time factor is divided by nt of a, which is just the number of times we've picked this action before. Now think about that. If we've tried an action a whole bunch of times, n is large, which makes this whole bonus term really small. We're confident about that action. But if we've barely tried an action, n is tiny, which makes the bonus skyrocket. It's like the formula is screaming, "Hey, pick me. You have no idea if I'm good or not." And finally, we have this little c. This is just a number that you, the programmer, get to pick. You can think of it as a knob that controls the agent's curiosity or its appetite for risk. If you turn C up, the agent will care a lot more about uncertainty and explore more aggressively. Let's make this concrete with a quick example. So action B has the highest estimated value, 2.2. A simple greedy agent would pick it every single time. But wait, look at its count. We've tried it 25 times already. We're pretty confident about that 2.2 value. Now look down at action C. Its value is only 1.5, but, and this is the key, we've only tried it twice. Because that count is so low, its uncertainty bonus is huge, giving it the highest overall UCB score of 3.1. So the UCBA agent very smartly chooses to explore action C to learn more about it. And what's the result of all this smart decision-making? Well, you can see it right here. Just like our optimistic agent, UCB, shown in blue, consistently pulls ahead of the plain old epsilon greedy method. By making these intelligent, uncertainty-driven choices, it just finds and sticks with the best actions way more effectively over time. It just works.
Okay, so we've seen a clever hack and a principled statistical method. Now let's get into our third and final approach, which comes at the problem from a totally different angle. Instead of trying to learn how valuable an action is, these things called gradient bandit algorithms try to learn a preference for each action. It's a whole different philosophy.
So here's the big mental shift you have to make. Action value methods, everything we've talked about so far, are like trying to put a precise dollar value on every item on a menu. This burger is worth $10, that salad is worth $8. Preference-based methods don't care about the dollar amount. They're just trying to create a ranked list. The burger is my favorite, the salad is second, and so on. The scores are just a way to keep track of that ranking. So you might be wondering, how do we go from a ranked list of preferences to actually picking something? Well, we use this awesome function called softmax. You can think of it like a converter. It takes our list of preference scores and transforms them into a set of probabilities that all add up to 100%. The action with the highest preference gets the biggest slice of the probability pie, but every action still gets a chance. And how do we learn these preferences? We use this really slick update rule. Now let's not get bogged down in the whole formula. I want you to focus on the most important part, right here in these parentheses. It takes the reward you just got and compares it to the average reward you've gotten so far. That average reward is called the baseline, and honestly, it's the secret sauce that makes this entire method work. The logic here is actually incredibly intuitive. It's very human. You take an action, you get a reward. Then you ask, was that better or worse than I expected? If the reward was better than your average, you increase your preference for the action you just took. If it was worse, you decrease its preference. And at the same time, the preferences for all the other actions you didn't pick get moved in the opposite direction to keep everything balanced. And this slide right here shows you just how critical that baseline is. It's not just a nice to have, it is everything. The top two lines are the algorithm's performance with a baseline. The bottom two are without it. I mean, the difference is night and day. And it's because the baseline provides context. It lets the agent know if a reward of +2 is actually good or bad. If the average is +1, then +2 is fantastic. But if the average is +4, then +2 is a total disappointment. The baseline lets the agent adapt. Okay, so we've looked at three very different, very clever ways to tackle intelligent exploration. Now, the big question isn't which one is the absolute best, it's more like which one is the right tool for my specific problem. Let's put it all together in a quick summary. Optimistic initial values. That's your simple, quick and dirty tool. It's super easy to implement and fantastic for forcing a lot of exploration right at the start, especially on simpler problems. Then you have UCB. This is your more principled, statistically sound option. It's powerful and effective, especially when you need to be very deliberate about how you handle uncertainty. And finally, the Gradient Bandit. This is your adaptable powerhouse. Its use of a baseline makes it amazing for complex environments where the definition of a good reward might actually change over time. And that brings us to the end. But I want to leave you with one final thought to chew on. Imagine you're building a product recommendation engine for a massive online store. New products are being added constantly. User tastes change with the seasons. Of the 3 methods we've talked about today, which one would you pick as your starting point to balance showing people things they already like with discovering new things they might fall in love with? And more importantly, why? Think about it. Thanks for tuning in.